All right, today we're going to look at the indefinite integral. And what the indefinite integral is a family of all the antiderivatives of f of x, which would be the indefinite integral. And it's denoted by the integral of f of x dx. Notice there's no upper or lower limit on this guy. And the time, this time when we work with the antiderivative for f for our function, we need to be sure to add a constant c. So we're really interested, what we want to work with, what we find the antiderivative of, is x squared minus sine x. That's our little f of x, and that's the guy that we want to find the antiderivative of. We want to find the starter equation, that capital F of x, that when we take derivative will give us x squared minus sine x. That's really what we're looking for here. And so we just kind of have to remember a few rules of antiderivatives, and one of them is, if you look at that x squared, maybe a pattern that you've noticed so far is that when we find that capital F of x, the pattern would be that we add 1 to the exponent with any polynomial. And then when we do that, we divide by the new exponent. So it's going to be x cubed now over 3. Then minus, and then the derivative of what is sine, okay? And with that, it's actually the derivative of negative cosine, which is sine. Not positive cosine, but negative cosine. So we end up with this as our antiderivative, as our capital F. Well, what does this mean? It means that the starter function, the function we took the derivative of, would be x cubed over 3 plus cosine x, because we can distribute that guy, plus, not only that, but plus any constant that could possibly show up at any point in time during the whole process. And so to talk about that constant, we just say c, okay? It could be 5, it could be negative 2 million, it could be 363,000. Who knows what it could be? But remember, the derivative of a constant, the derivative of that constant right there, is always going to be 0. So it doesn't really matter what constant we put in its place. It just matters that we have one, okay? For example, if I take x cubed over 3 plus cosine x minus 2, and remember this is my capital F of f, if I take that guy and find derivative, then what I'm going to end up with is x squared minus sine x, okay? The derivative of negative 2 is 0, all right? Or we could look at another just real quick example. Again, capital F of x equals x cubed over 3 plus cosine x. So if I've got this guy, what if I added negative pi? And remember, pi is a constant. Even though our brain doesn't want it to be constant, pi is a constant. So when I take derivative of this guy, I get x squared minus sine x, and the derivative of pi is 0, okay? So that's that c value that we're talking about that we have to have every time we look at the antiderivative, okay? The negative pi is c. That 2 right there, that is c. And the derivative of all of those guys is going to always be 0. So we just have to represent all the possible things that c could be in this way, okay? Okay, on this slide we're looking at some super duper really handy patterns and rules for finding integrals, finding indefinite integrals. And so it's just really important to understand that these are patterns. So we're looking for different things. And if you look like at this first example right here, this first pattern, this is one that we just did where you've got the variable up as a number. We're going to add a number and divide by that guy when we come out of the integral. If we integrate sine, we get negative cosine. If we integrate 1 over x, we get natural log of x. If we integrate all these different things, what comes out is what we equal. That gives us our starter function, our capital F. Now, one thing not listed on this chart that you want to make sure that you write down, and if you're one of my kids, you can put this on your trig cards, on your trig sheets. These are important things. But the log of base ax, where a is a constant, okay? If we are going to integrate this, we're going to use a little, conversion here, where we're going to look at the natural log of x over natural log of a. Remember, you can rewrite that, you can change your bases, okay? And where natural log a is a constant. And so now what we have is the natural log of a times 1 over the natural log of a times the natural log of x. Well, that integrates out to x, natural log x minus x over the natural log of a plus c. And remember, a will be constant, okay? So in all the things that you do, a will be constant. The x will be your variable in this one, all right? And so this is a really important sheet to have. Make sure you've got all these formulas written down. You're going to use them just a ton. All right, what we're going to do on this slide is setting up our substitutions for integrals so that we can understand what's going on. We're going to look at some different things here because at some point in time we're going to have to work with the chain rule. And remember when we took derivative with chain rule, there was a lot of stuff going on, okay? And so this example then just kind of sets our ground rules for that. So we're going to let f of x equals x squared plus 1. We're going to let u equal x squared. So find each of the following. Now, first step, when we take this integral, we need to make sure that all of the variables are the same. So f of x dx, that's good. F of x dx is good. That means that we're ready to integrate. So we go ahead and do that. And we're going to add 1 to the 3, and we're going to divide by that new number. Okay? So as long as I've got x cubed and a dx at the end, life is nice. All right? So here we go. X to the 4th over 4 plus x. And then plus c, because we want to account for all the different possibilities that our constant could be represented with right there. Okay, next up is f of u du, all right? And so what does that mean? Well, we just substitute in our u now. So we're looking at the integral of u du. And that's all that we know at this point in time, okay? And what does that mean? Well, u goes in for that x in f of x. So it's going to end up being u cubed plus 1 du because it says, okay, that we're looking at this function of u. The only function we have is x cubed plus 1. Now, again, the u's match. So since u cubed and it's du at the end, I can go ahead and integrate. This isn't a problem. And I just follow all the integration rules from that slide we just saw. So in this case, I'm going to add 1 to the exponent, divide by the new exponent. So it's going to be u to the 4th plus 4 over u plus u plus c. All right? So these first two guys are identical. The only thing different is the variable on the inside. That's it. But if you look at this last guy over here, this says f of u dx. All right? Those variables are not the same. And so what is it that we're looking at specifically? Well, we're looking at u cubed plus 1 times dx. But I can't integrate this. In order to integrate this, I have to have the u and the x be the same exact variable. That's the only way to get around that problem. Well, lucky for us, we have an equality statement for u, and that is that u is equal to x squared. So right there, I'm going to let u be equal to x squared. So everywhere I see u, I put an x squared in its place, and that gives me my substitution. My integral then becomes x squared cubed plus 1 dx. And now I've got everything together to integrate because the variables are all the same. So the function I'm going to be working on is x to the 6th plus 1 dx. And I follow, when I integrate this, I do everything that I've done in the past. I don't make any big changes at all. The x's are there, x to the 6th dx. So I add 1 to the exponent, divide by that new number, which is going to give me x to the 7th over 7 plus x plus c. And that's all there is to it. Now, it looks really weird. You may have to watch this a couple times, but it really isn't a bad thing. And it allows us to handle the chain rule, which is really important because a lot of those derivatives and integrals that we look at have the chain rule included in them in some way. Okay, so let's try out some substitution then with integration. And keep in mind that what we have to do is work with the whole derivative of what thing is going to be what item, the f of x du part. So here's what we're going to do. When we look at this question right here, sine of x e cosine x, remember that the derivative of e to the x is e to the x. So he doesn't ever change at all. But there's a relationship here between the sine and the cosine. One of those is the derivative of the other. And in this case, u, if we let u equal cosine x, then du is equal to sine x. Du dx is equal to sine x. Okay? And if you don't see that right away, that's okay. It's going to take some practice to get this comfortable with it. All right? So the derivative of u is du dx. That's going to be sine x. Now, if I multiply both sides of this equation by dx, because we're going to treat it as a fraction, then what I end up with is this. Du equals sine x dx. Now, here I have a sine x dx. Here I have a u. And so now what I can do is I can rewrite my integral, and I can use it with these u's that in there now. So instead of sine x e cosine x dx, I can write e to the u, because u is cosine x, times du, because du is sine x dx. So it's a straight up substitution, okay? And now when I integrate this, when I integrate e to the u, I just get e to the u plus c. We love integrating the exponential function, okay? Now, one last step to finish, and that is this. We've got this u right here. We've got him right there, and we've got him right here. So to finish this problem up, we're just going to make that substitution. E cosine x plus c, and we're done. All right, so let's look at the next problem here and find an integral of x squared times the square root of 5 plus 2x cubed. So one of these is the derivative of the other, and let's look at it as kind of two pieces. We've got 5 plus 2x cubed here, and then we've got x squared out here. Now, which one could be a derivative? That's the question that we want to ask. And I would say that if we look at 5 plus 2x cubed, and then if we look at the derivative of that, that this is going to be 6x squared. And so what we want to have is we want to have this dx inside of our integral. So we're going to go ahead and multiply both sides by dx. And that's going to end up giving us du equals 6x squared dx. Okay. Now, what kind of integral situation is happening? This is what's happening. I've got a u underneath my radical. So I've got the integral of the square root of u. And then notice that I've got x squared dx, but I have x squared dx. So I need an equality statement for that. And if you'll look where we have du equals 6x squared dx, the 6 can't stay over here. So what I'm going to do is I'm going to divide both sides by 6. And so 1/6 du is equal to x squared dx. Now, this x squared and this dx have an equality statement now with 1/6 du. So times 1/6 times du. And when we work this problem out, what we're going to end up with is the 1/6 can come in front of the integral because it's a constant. U is 1/2 du. Now, add 1 to the exponent, divide by your new number. So I'm going to have 1/6 times u to the 3/2 divided by 3/2 plus c. All right, and there's your integral part. So to finish this guy up, all we would do is we would clean up the fraction. So we're going to have 1/6 times the reciprocal, 2/3 times u to the 3/2 plus c. And lastly is just to reduce this guy all the way down. And this is going to end up being 1/9 u to the 3/2 plus c. So a few more steps in this one because of how our u, when we did our derivative of our u, kind of how it had to go. So there you go. There's that guy. and pause the video or whatever, and we'll do the next one.
All right.
All right, last one, cotangent 7x dx. I cleaned off our slide here because this guy is more involved than you think. And when you go through and look at what we've got, we don't have anything that derives to cotangent. So we're going to have to work substitution a couple times here. But when you're given a trig function, the first place to start is inside the trig function. We're going to let u equal whatever is inside there. So when we take our derivative, du dx equals 7. We solve for the du, 7 dx. And then keep in mind, we want 1 dx. Okay, and so to get that guy, we're going to divide everything by 7. So 1/7 du is equal to dx. There's my equality statement. Now, what's this look like? It looks like cotangent u du. But with cotangent, we don't have a specific derivative, antiderivative of this. So we're going to have to sort this out. And what we're going to do is we're going to do another substitution. But first, let's break it up into cosine u over sine u du. Okay? And then, I know this is going to be a killer, but we're going to use w. Okay? And let's let w equal sine u. And the reason I say this is because the derivative of that is the cosine. And anytime you make a substitution, you want something that derives to the other piece. So dw is equal to cosine u du. And look what I have right here on the top. I have a cosine u du. So that changes my integral one more time. And I know this is really crazy, but just hang out with me for just a minute. So what I end up having here is 1 over w dw. Now this we can integrate, all right? And so when I integrate this, this is going to end up giving me the natural log, and there should be a 1/7 in here. I forgot that guy right here. Here's my 1/7. So this should be 1/7 here, 1/7 here, 1/7 here, and so 1/7 here. Natural log of w, okay? The natural log of w, we want it to always be positive because you can't take the natural log of a negative, is sine u, all right? And what is u is 7x, so this is going to be 1/7 times the natural log of the absolute value of sine 7x. So it takes a few steps to get there, but there we are nonetheless. We use 2 substitutions on this. And if you need to watch it again, watch it again. This can be a little bit of a tricky thing to sort out the first time you see it. All right, so here we go. Substitution now with trig identities, all right? And so what we're going to do is let's just look at this first guy right here where we've got dx over cosine squared 2x. And remember that what this really is if we think about cosine squared 2x, that's the same thing as secant squared 2x. So what we're really working with here is the integral of secant squared 2x dx. But again, when we start to do our integration, we can't handle just a 2x in there. We've got to sort that guy out. So we're going to let u equal 2x. du is going to be du dx is equal to 2. So du is equal to 2 dx. And remember, we want an equality statement for just dx, okay? Look, I've got secant of u. I've just got 1 dx, so I just need just dx right here. And that's when I'm going to divide both sides by 2. So d, or 1/2. Multiply both sides 1/2 or divide by 2. So that gets me this part. What I'm going to integrate then looks like this. 1/2 of secant squared u du. Okay. Now, this one we can do. The 1/2, since it's a constant, can move in front of the integral. So it's 1/2 secant squared u du. And secant squared is one that we know. In fact, it's on that little handy-dandy list of rule sheets in if memory serves correctly, it's tan u. So 1/2 tangent u plus c. Oh, by the way, u has to be replaced. So my final answer then is going to be 1/2 tangent 2x plus c. And if you take the derivative of that, you'll be good to go. It won't be a problem at all. Okay? What about this next guy, cotangent squared of 3x? Well, if you look on, on whatever trig resource you have with different trig identities, cotangent squared of 3x is equal to cosecant squared of 3x minus 1. Okay, so we don't have anything that works us out with cotangent squared, but we do have stuff that works us out with cosecant squared. So my integral on this guy then is going to end up being cosecant squared of 3x minus 1 dx. All right. Well, how do you handle this situation? We can let this guy right here be equal to u. So u equals 3x. du dx is equal to 3. So du equals 3 dx. And 1/3 du equals dx. So there's our equality statement. And again, because we just have the one dx right here. Okay, so let's go ahead and sort this out. And this guy's a little bit interesting because we can actually look at this in two ways. We can look at this as cosecant squared 1/3 cosecant squared of u du minus 1 dx. Okay, and why can I do that? Because when I integrate, if I have a plus or minus sign, I can separate my integrals into those different pieces. So that's what I've done here. And now we can integrate. Well, if you integrate cosecant squared, you end up with negative cotan. So this guy's going to be negative. So 1/3 times negative cotangent of u minus, and then the antiderivative of 1 is just x. And then what is u? U is 3x. So 1/3, negative 1/3 cotangent of 3x minus x. So there's the first two guys. I'm going to need a little bit more room for this third guy, so I'm going to pause the video, clean this up a little bit, and work out this third one, which is a little bit more involved. Okay, so on this last guy, some more trig identities here to integrate. And what I'm going to look at with this cosine cubed, we don't know anything that integrates to cosine cubed. So what I'm going to do is I'm going to take cosine cubed and split it into cosine squared x times cosine x. And one of our trig identities is with cosine squared x, where it's going to be 1 minus sine squared x. And so what I'm going to actually integrate then is the integral of 1 minus sine squared x times cosine x dx. All right, now on this one, when I'm trying to figure out what u should be, I'm going to look at where the power is located. So my power is located right here with sine, okay? So if I let u equal sine x, then du dx is equal to cosine x. And if I get du all by itself, I have cosine x dx. So check it out. What I need is cosine x dx. I can replace that inequality with du, and then I can place a u for my sine squared. So here's my new problem. 1 minus u squared du. How about that? Okay. And when I integrate this guy, then I'm actually integrating 1 dx minus u squared du. Okay. Antiderivative of 1 is just going to be x minus, antiderivative of this guy would be u cubed over 3 plus c. Okay? Now, what is u? U happens to be the sine. So this is going to be x minus sine cubed of x over 3 plus c. And that's all there is to that guy. He's really not too bad at all, but it's a little bit of a trickier move than what we've had to do in the past because you've got to break that cosine cubed up. But there you go. All right, now how do you use all the substitution business when you've got definite integrals running around? Well, have no fear. I know exactly what to do. And so here is what we're going to do. Looking right here at this first guy, one of these is the derivative of the other, okay? And when I'm looking at this, I'm thinking that if I start with tangent and differentiate that, I'll get secant squared. So I'm going to let u equal tangent x. And that means that du dx is going to be secant squared x, which makes du equal secant squared x dx. All right, no problem, right? So my integral then becomes the integral of u du. How great is that? Here's u right here. Here's du right here. So all that sorts itself out really well. But what about my limits of integration? What do I do on that? Well, all you have to do on that guy is substitute into u our values. So I'm going to do two things here. All right. I'm going to do the tangent of 0. And I'm going to do the tangent at pi over 3. Okay. Because what's going to happen is when I do the tangent of 0, that's going to be 0. That takes this place right here. Okay? And when I do the tangent at pi over 3, that's my upper limit of integration. Then whatever that turns out to be, which in this case is square root of 3. Tangent of pi over 3 is the square root of 3. So the cool thing about what we just did is we don't have to unsubstitute at the end. We don't have to substitute back in. We can just take derivative, the antiderivative of this guy, find the antiderivative of this guy, and then use our new values for our upper lower limits, and we're done. So here's what it would look like. U squared over 2 evaluated from 0 to radical 3. What does that mean? That means I evaluate this from radical 3 squared over 2 minus 0 squared over 2. And that gives us 3 halves minus 0 or 3 halves. There's no going back in and messing things around. There's no resubstituting back in. Once we put this 0 right here, once we put that 0 in for this x, and once we put this pi over 3 in for this x, we are done with all our substitutions. We're finished. Okay? Well, what about this last guy? So here's what we're going to do. Look for something that's the derivative of something else. So here's x. So I'm going to let u equal x squared minus 4. Okay? Du dx is going to be 2x. Now watch, the hand is quicker than the eye. We've done this a lot of times. I need dx to be equal to something. So I'm going to divide by 2 and multiply by dx. That gives me my x dx right here. All right. My equality statement then, my equality integral becomes the integral of 1 over u, because here's x dx, that's du part, so 1/2, okay? And then 1 x dx, which is du over u. Now, I don't want to have to resubstitute and do a whole bunch of stuff. So the next step I'm going to take is I'm going to put 0 in here for x. Okay? So when I do that, I get 0 squared minus 4. Okay, that gives me a lower limit of -4. And then I want to put 1 in for x. And so that's going to give me 1 squared minus 4, which is going to be -3. So this integral that I'm going to now evaluate is going to go from -4 to -3, and it's 1 over u du. So how does that guy integrate? I'll just slide it this way so we've got a little bit more room. It integrates to 1/2 times the natural log of u evaluated from -4 to -3. Remember, 1 over u, when you antidifferentiate that, is natural log u. So now, to finish it up, we're just going to have 1/2 times where we stop, which is natural log of -3, minus where we start, which is natural log of -4. But you can't take natural logs of negative numbers. And so what this is really saying is no bueno. But if you notice, we've got natural log of -3 minus natural log of -4. We can divide those, all right? So that's 1/2 times natural log, times the natural log of -3 over -4, and the negatives divide out, because negative divided by negative is positive, so it's 3/4. And there you go. There's some substitution with your upper and lower limits of integration.